Good morning, everyone. Just getting set up. Good to see we have most, half, something like that of y'all in here. And you'll have to forgive me. I'm still getting used to this little tablet. So I'm a little slow with the writing. Just going to put a few random things up here for now while we're still waiting. All right. So again, welcome back. I know this is kind of an unusual format, but we live in an unusual time for the moment. So we're going to make the best of what we can. The good thing here is everything is going to be recorded. I'm going to be uploading videos to YouTube and then posting them in the Canvas shell. Just want to show that for a second. The little menu needs to move out of the way. So in our Canvas shell, and I'm assuming y'all have already figured this out, but there's the live lecture link. I just did a short test stream a few days ago to make sure everything was working proper. So this was a link to a YouTube video. So each day I will, after I've finished the lecture, I will upload to YouTube. I have to wait for everything to convert, it takes a few minutes, and then I will add a new tab to this, and I will have the date on it. I might be able to put the section as well. Hopefully I'll be able to do that. We do have our test on chapter 6 that's going to be coming up soon. We're going to be finishing 6.3 today. We're probably going to be working on 6.5 Wednesday and Monday. So I'm thinking the week of the 6th, test 2 will be posted in my math lab. You will still get a review, and the review will still be similar to the test. So all of that stuff will still be the same. We just won't be taking the test inside of a classroom. You'll be doing it at home. It'll have a time limit. I'm going to give you 2 attempts, and I'm going to write all this stuff down in case anyone misses it. So without further ado, let's pick up where we left off. And that was in 6.3, the double angle. Double angle. And half angle formulas. And again, I'm sorry about the handwriting. I'm gonna get used to this thing. I requested a document camera, but they haven't been able to get it yet. So as a reminder, we were working on the half angle formulas. The sine, we had that the sine of theta over 2 was going to be plus or minus. It was one or the other. And then we had a square root, a bigger square root than that, of 1 minus cosine of, and you double the original angle all over 2. Now that 2 is inside the radical. Let me just extend that a little more. There we go. Then we had that the cosine of a half angle is plus or minus, and again, 1 of, and that's based on what quadrant the original angle you're given is in. And that was a big square root. And it was pretty much the same except the plus in the top. 1 plus cosine of twice the original angle all over 2. And then I believe I gave y'all, and it's been a while, I believe I gave you the version for tangent that looks like this, and I mentioned that there's a better one So this goes big old plus or minus square root 1 minus cosine of the doubled angle over 1 plus the cosine of the doubled angle, which you can basically see is just the sine over the cosine, because the 2's and the denominators would cancel each other out when you do your compound fraction. But there's an easier version, and this is the one that we're going to use in the next example. So tangent of a half angle is going to be, and there's two versions of this, 1 minus cosine of your doubled angle over just a sine of the doubled angle, and there's no square root, there's no plus or minus here. Or you can use, that's an or, not an on, sine of theta over 1 plus cosine of theta. Now again, when we're talking about theta here, these are twice the original angle. So if you were trying to find the tangent of 15 degrees, you'd be using 30 degrees in these formulas, and same if it was a cosine or a sine. So again, these are the ones that I would say to use right here. These are better because this is just a lot of evaluation, especially with the square root, especially having the plus or minus. Now, I believe I mentioned in class that I'm not going to make you memorize these formulas. All of these will be on your formula sheet, and I'm going to start preparing that and get that sent to y'all very, very soon so that you'll have it for your exam. But for now, let's move on and do an example. And the last example we did in class was example 4B. So just as a reminder, example 4A, we found the cosine of 112.5 degrees. So when we did that problem, we doubled the 112.5 to 225 because that's when we knew how to handle. B was the sine of 15 degrees. And we doubled that to make it 30 and used the appropriate formula. But we're going to actually focus on C, the tangent of 22.5 degrees. So this is the example we're going to do. Sorry about that. There's an extra button on this pen, and it throws me off. So you could use that plus or minus square root formula. You most certainly could, and I'm going to go back a screen. You most certainly could do it with this formula, but I'm not going to because using one of these two on the bottom is easier. And depending on the problem, the first version could be easier, the second version could be easier. I believe that for this one, the first version is going to be easier because there's only one piece in the denominator. So we're going to say that this is equal to 1 minus the cosine of 45 degrees. Where did 45 come from? Because I doubled 22 and a half. So 2 times 22 and a half is 45. And we know how to handle 45 degrees. I even wrote that triangle over here with my nice pretty handwriting. So you got your 1, 1 square root of 2 triangle. So we're going to be using that guy. So 1 minus cosine of 45 over, let's finish the formula, and that should just be a sine of 45 degrees. And we know that the cosine and sine of 45 degrees are both 1 over square root of 2, but 1 over square root of 2 is square root of 2 over 2 after you rationalize. So this is going to become 1 minus square root of 2 over 2. Again, that's the cosine of 45. And then the sine of 45 is also square root of 2 over 2. And that's because the adjacent and the opposite are the same value, 1. So there's no square root, there's no plus or minus. We didn't have to figure out which quadrant this was in, which it would have been in quadrant 1. But we have something that needs to be rationalized, and we have a compound fraction. So we're going to have to handle both of those issues. Actually, it doesn't need to be rationalized yet. We'll handle the compound fraction, then rationalize. I just said it backwards. So we have denominators of 2, these individual denominators. So to clear that, we say that our LCD is 2, and we're going to multiply the 1, the square root of 2, and the square root of 2 by that. So we're going down here. So we got 2 times the 1 minus 2 times the square root of 2 over 2, and all over 2 times the square root of 2 over 2. I wish I had a way of quickly switching between colors. Maybe I'll figure that out. So the reason we do that is because these 2's will cancel. And these 2's will cancel so that they're no longer compound fractions. So now all we have is just 2 minus the square root of 2 over the square root of 2. Now this bottom has only got a single square root. There's no plus or minus, so we don't have to multiply top and bottom by a conjugate. We just need to multiply top and bottom by what the bottom is, by that square root of 2. So we multiply, now I'll make sure we take an extra step, 2 minus square root of 2 over square root of 2. We multiply the top by square root of 2, we multiply the bottom by square root of 2. And since this top has 2 terms, you might want to wrap it in a parentheses so that you can show the distribution. So that'll give us 2 square root of 2, distributing to the first, 2, minus, that's going to be a square root of 4, because both of those 2's are inside the square root, all over another square root of 4. But each of those square roots of 4 is 2. That's 2 square root of 2, minus 2, all over 2. And we're almost done, but you can see that every single factor outside of the radical, every single term, has a 2 in common, so we can reduce. We can take 2 from each of those. So that's 2 square root of 2 minus 2 over 2. Each of these 2's divides out and becomes a 1. And we know that if the denominator is a 1, we don't even need to write it. So that's just the square root of 2 minus 1. And that is our answer. So again, this was just a half angle problem. We had already done all of the double angle stuff before, so check your notes for those formulas. It would take me a very long time to write them out. I'll just kind of say them. The first one was the sine of 2 theta was equal to 2 cosine of theta times this. I think I said that wrong. Let me start over. The sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. Then we had 3 versions for the cosine of 2 theta. The first one being cosine squared of theta minus sine squared of theta. And then the tangent of 2 theta was 2 tangent of theta all over 1 minus tangent squared of theta. And I had said that you need to memorize the sine of 2 theta formula, but that I would give you the cosine formulas and the tangent formulas. So I'm going to give you all the half angle formulas. I'm going to give you most of the double angle formulas. The only one I won't give you is the sine of 2 theta. So just as a quick reminder, you need to memorize that the sine of 2 theta is 2 sine of theta cosine of theta. The rest will be on your formula sheet that we covered in the section. When you look in the section, you might see some indifference formulas. We're not going to use them in this course. It was something that I would have talked about in class briefly, but we lost a week, so we're going to skip that. The same thing goes for 6.4. I was going to have a little mini talk, even though we don't have any homework on 6.4, on the usefulness of product to sum versus sum to product formulas. But again, we lost a lot of time, so any material that was, I guess, extracurricular, we are going to pass by. So there we go. All right, so we're gonna get 6.5 going in just a minute. I just need to set something up. All right. So I got a little bit of typing to do. 6.5. And we'll make this font a little bigger. 6.5, trig equations. So a couple reminders. Sine, cosine, cosecant, and secant all have a period of 2 pi. And I'm just going to write the letters pi instead of the symbol here to cut some time. Whereas tangent and cotangent have a period of pi. So that's going back to our first chapter when we talked about the periodicity of the functions, and that for tangent and cotangent, everything happens in quadrants 1 and 2 and then repeats exactly in quadrant 3 and 4. Whereas the other 4 trig functions, because of a smart trig class, because of the plus or minus patterns as you go around, there is no repeat until a full 360 degrees. So again, 2 pi is 360 degrees, pi would be 180 degrees. So in dealing with equations, if your solutions have a domain that isn't restricted, you must consider the periodic nature of these functions. That isn't restricted. What does that mean? Well, we'll see that in the examples, whether there are restrictions or not. So think back to the first chapter when we were limited from 0 to 360 degrees. That's basically what we're talking about here. Or maybe we were limited from 0 to 180 or from 90 to 270. So sometimes there are restrictions in problems, and sometimes there aren't. Well, when we're dealing with these equations, if 0 degrees is a solution because of the periodic nature for sines, cosines, cosecants, and secants, if 0 is a solution, that means 360 is a solution. Then you can add another 360 to get another solution. Then you can add another 360 to get another solution. So there's actually infinitely many solutions, and we'll have to take this into account for some problems. But other problems will say, just give us the solutions in quadrants 1, 2, 3, and 4, or between 0 and 360 degrees. So then that will be less of an issue. And again, tangent and cotangent, it would be 180 instead. So what are these restrictions? For sine, cosine, cosecant, and secant, you're going to add 2 in pi, where in is an integer. To each solution if unrestricted. So 2 times in times the symbol for pi, not the letters. So then for tangent and cotangent, you're just going to add in pi. So that's in times pi. Again, in is an integer, and an integer just means it's like a whole number, but it could be positive or it could be negative. Oh, okay. I'm seeing some questions. I'm glad that someone mentioned that. You're not seeing what I'm typing. So let me screen. Can someone in the chat please answer that is up there now? Okay, it wasn't frozen. I have to change my screen share. Thank you very much. See, these are the complications that we have to learn to deal with. So I'm gonna leave this up here for a minute to give y'all a second to type. I apologize. So again, these are just some conditions for the equations that we'll be solving. And sometimes this will add in pi or add 2 in pi. It's not even going to be necessary. It's based on what the original problem asks us to do. And when we see our examples, you'll see the differences. So because sine, cosine, cosecant, and secant have a period of 2 pi, you're going to add 2 in pi to the solutions, where in is a variable representing a number like 1 or -3 or 0 or 2. In fact, it represents all of them. So in can be -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. It's all of them. But then for tangent or cotangent, because period is half of that, we're only going to add in pi. Again, that's every multiple of 180 degrees. So 2 in pi is every multiple of 360. In pi is every multiple of 180. Okay, so some techniques. So when you are asked to solve a trigonometric equation, remember like when we had to verify identities, I gave you a whole bunch of techniques. I'm going to give you a bunch of techniques here. If there is only one term, one trig term, isolate it. Let me go back and do this. There we go, get a little more space. So if there's only one trig term, if there's only a single sine or a single tangent or a single cosine, then isolate it. Now, what I mean is one type of trig term. So maybe there's a sine on the left and a sine on the right, or a cosine on the left and a cosine on the right. So if there's only one type of trig term, isolate it. Next up, if the inside of the function, of the trig function, is not just x or theta or a single variable, you're going to have to do this n equals 0 through 1, 2, 3, etc. kind of case. And I know that's not going to have any kind of reasoning yet. We're going to have to wait till an example. But the basic reasoning for this is, if you remember when we were graphing trig functions, having a number in front of your variable made it to have a quicker period. So if you had a 2 in front of it, it was going around twice as fast. So going through these n equals 0, 1, 2, 3 cases, and it may be more, it may be less, that's going to account for the fact that we're going around a full circle more than once. So that's until you go past one period. Again, we'll have that be seen in an example later. If you ever have anything that you can factor, general rule of thumb in math is if something's factorable, it might be a good idea to factor it. So with factoring, you may end up using your zero product rule. You may end up leading to multiple equations in this single trig equation, just like quadratics and cubics. You may need to use Pythagorean identities. You may need to use double angle formulas. You may need to use some other properties. Thank you, Ward, for fixing my typo. Then, when you end up solving your equations, you have to watch out for, this is a fancy word, extraneous solutions. Remember, extraneous means solutions that you find in the process, but when you actually think about them, when you analyze them, when you maybe check them, they don't actually work. And this can also be circumvented by recognizing ahead of time, hey, this isn't possible, so I know I don't even need to have to try and solve this. And we're going to see this happen. And then the biggest issue for that extraneous case, so I'm going to put a little asterisk, and this goes with the extraneous solutions. Mainly, sine and cosine are bound between -1 and 1, the outputs, that is to say. Remember that for a sine, the largest output is 1, the smallest output is -1, the same for cosine, and this is from the previous chapter when we were graphing them. Those waves, the highest they ever were 1 and -1, unless there was an amplitude value up there. Now, notice I said mainly, that's not everything, but it is the biggest issues that we will come across in Math 162. So again, some of the biggest issues we'll have in this section is whether the question has solutions that are restricted or not. So if they're unrestricted, in other words, if I just give you the equation and I don't say on some interval, then you'll have to do this add 2n pi or add n pi stuff. If I do give you restrictions, we don't necessarily have to add those unless we have an not an amplitude factor, a period factor inside. In other words, a number in front of the variable. Okay, so with that being said, let us try out some examples. So let's go back to the whiteboard. So I believe if I do new share, whiteboard, that'll take us back over here. Cool. So let's go to another page on the whiteboard. Move this. Yes, that's going to be a lot easier if it's down there, and y'all probably can't even see me move that. So this is 6.5. Let me get my pen back. Trig equations. And then we're going to start with example 1. We're going to just say solve. We got, excuse me, 3 times the sine of x minus 2 is equal to 5 sine of x minus 1. So if you think back to your notes, and just so I don't have to keep switching the screens, we said that if there's only a single trig term, to isolate it. And that's what we mean by here. There's a sine of x and there's a sine of x. There's no cosines, there's no tangents. So this is kind of an optimal situation. So we just want to isolate it. We're going to pretend like it's an x. Move all the signs to one side and move anything that doesn't have a sign to the other side. Now, it technically doesn't matter which way you move the sine of x, but I'm going to treat this kind of like how most people treat equations. We like to keep the variables positive when possible. So let's subtract 3 sine of x on both sides. Again, I'm sorry about the lack of different color. And then that will give us -2. The -2 is still on the left side, equals. That's like 5x minus 3x, but with a fancier x. So that's going to be 2 sine of x minus 1. So now there's only a single sign on the right side, but now this -1 and the 2 being multiplied, we need to get rid of them. So to do so, we add 1 to both sides, which will give us -1 is equal to 2 sine of x. And then we want to divide both sides by 2, which will give us -1/2 is equal to sine of x. So we now have the sine term isolated. So if this was just x, we'd be done. X equals -1/2, but it's not. It's more complicated than that. So we're saying that the sine of x is equal to -1/2. This is the equation we're solving, and we have done this in the past chapter. And we didn't even use inverse trig functions. You can, and we're not going to now, but we're just trying to find all x's. Oops, let me undo that. All x's that would make the sine, in other words, the opposite of the hypotenuse, -1/2. So we have to think about the quadrants. The negative puts it in quadrants 3 and 4. That is a Roman 3, sorry for the sloppiness. And that's by a smart trig class. That's the unit circle, the quadrantals, and sine going like the y value, and y is negative in quadrant 3 and 4. So we can use a reference triangle for this. Where here's our x, that's our angle, and the opposite should be the 1, the hypotenuse should be the 2. So that is, I hope, clearly the 1, 2 square root of 3 triangle, which we had written up here originally. So that means that x, and I should use an x prime for this since it's a reference angle. Since it's opposite the 1, that has to be our 30 degrees, and I'm going to use radians, 30 degrees being pi over 6. So our reference angle is pi over 6, but we're in quadrants 3 and 4, so we need to put that in quadrants 3 and 4. Just go up here. So in quadrant 3, that's where we have to do 180 plus the reference angle, 180 being pi. That's pi plus pi over 6, which when you get an LCD is 6 pi over 6 plus pi over 6, which would be 7 pi over 6. And then for the quadrant 4 answer, excuse me, we have to do 2 pi minus the angle, the reference angle, that is to say, so 2 pi minus pi over 6, which getting an LCD, 2 pi is 12 pi over 6, with the original denominator 1 goes into 6 twice, 1 goes into 6 times, 6 times 2 is 12, and then that's minus our pi over 6, which there's an imaginary little 1 here, an implied 1, and 12 minus 1 is 11, that's 11 pi over 6. So these are the two answers from 0 to 360 degrees inside of just one revolution of the circle. But going back to the problem, all we said was solve. There were no restrictions here. So there were no restrictions to the domain, so that whole add 2n pi or add n pi situation is in effect. Now, because we're dealing with solutions involving sine, we're going to add 2n pi to both of these solutions. So that's this. Our solutions are x equals 7 pi over 6 plus 2 times n times pi, or, that's semicolon, 11 pi over 6 plus 2n pi. And again, what adding the 2n pi does is, all right, if n is 0, then that term's not really there. We just have the original solutions in the first revolution. If you let n be positive 1, we're essentially adding 360 degrees. So now it's, what's that, 210, and then 210 plus 360 would be 570, and then you could add another 360, add another 360, add another 360. You can also subtract because n can be negative. So -1, -2, -3, that means we can just continuously subtract 360 degrees. So these are infinitely many solutions represented right here. So because there were no restrictions in the original problem, we have to add this 2n pi, and that can cause people to lose points or get a question incorrect on a test or a homework problem. And what would the restrictions look like? Well, of course, we'll see that in an example coming up, but not the next one. All right, so I'm going to give that one more minute just to kind of soak in, let you copy things down. Okay, so let's move on to example 2. And this is going to be solve tangent of x minus the square root of 3 is equal to 0. Now again, all I've said here is solve. I did not give any restrictions. So if there was a restriction, it would be after solve. I would say something like on this interval, and I generally do it in interval notation. So again, that's something we'll be seeing, well, soon. But for now, this just says solve, and this is a tangent. Well, I only see a single trig term, so that was the first technique. Let's isolate it. So we should probably add square root of 3 to both sides, which will give us the tangent of x is equal to square root of 3. And that's it for that part. The tangent is now isolated. So tangent, SOHCAHTOA, tangent is opposite over adjacent. So in the last example, when it was -1/2, that told us the opposite was 1, and the hypotenuse was 2 because it was a sine. This is a tangent, but I only see the top part of the fraction. So what you may want to do is say that this is the square root of 3 over 1, because any number can always be written as a fraction over 1. Now tangent, TOA, is opposite of our hypotenuse, so that says the opposite is the square root of 3. The hypotenuse is 1. So we can draw up a triangle. That is terrible looking. Let's try that again. So here is our x. Now, because this is positive, I don't have to use a reference angle here. It will be the actual angle. It would be in the first quadrant for the triangle. And then its opposite being the square root of 3. Its adjacent being the 1. And then the hypotenuse, this is the 1, 2 square root of 3 triangle. So the hypotenuse is 2. This, of course, is our right angle. So by memorization, and I'm not going to flip back, we know that this would be the 60 degrees, or in radians, pi over 3. So this time our angle in quadrant 1 is pi over 3. So that will be our first solution without the period factor being added. But then we had to say, oh, okay, well, tangent's positive in quadrant 1 and 3. That's a positive, not a 7. It looks like 70. That says tangent is positive in quadrants 1 and 3 by a smart trig class. But we only need to consider quadrants 1 and 2 since it has a period. I think I missed a letter in there. Period of pi. So we don't have to even put this in quadrant 3 because when we add the n pi, that's going to actually put it in quadrant 3. And then we add n pi again, it puts it in quadrant 1 and then back to quadrant 3, and they'll keep bouncing back and forth. All right, so the period is pi. And let's go back up here. So again, this was not a restricted. So since this is unrestricted, we have to add in pi to the solutions. This isn't a sine or cosine or secant or cosecant. Those you add the 2 in pi, tangent and cotangent, you have to add in pi. So our solution would be x equals, that's a colon, not a question mark, pi over 3 plus in pi. So again, what that in pi is doing here is adding every single multiple of 180 degrees. And every time you add 180 degrees, you go from quadrant 1 to 3, then back to 1, then back to 3, then back to 1, then back to 3. Or you could let the n be negative, and it's the same thing. You're just going you're going clockwise instead of counterclockwise. So again, both of these problems did not have any restrictions. All it said was solve. So when all it says is solve, you have to add in this n pi or 2 in pi, always. And this is a very common mistake people make on handwritten tests moving forward. Since we're taking tests in my math lab, this might be less of an issue. We'll have to see. We will see. So I'll leave that up there for another 30 seconds. All right. And let's go back to the type notes, and I need to remember to share that screen again. So this is after example 2. when the inside is 2x, 3x, 4x, any multiple of x. This is what I mentioned earlier. This thing, this right here. The inside of the function is not just an x. A substitution is a good idea. We'll say let theta equal the inside. The actual letter, don't use the word when you're doing your problems. And then you will find all theta that solve this equation. Convert back to x after you get your solutions in theta. This is like I talk about, I give you a problem in dollars, but you convert it to yen, but I want the answer in dollars. So when you go to theta, that's the yen. So you'll solve that, but I still want the answer in terms of the original variable, so you have to go back. But when you go back, this is where you do your n equals 1, 2, 3, until you're outside 2 pi. What's going on here? Why is this? So again, a value in front of the argument, your x, it causes the trig function to move more rapidly. It makes it faster. You get more waves in the same amount of time when you go and graph it, which means we're going to get 2 times as many solutions, or 3 times as many solutions, or 4 times as many solutions than what you might think are actually there. So that's why we have to do this n equals process. And I started at 1. I actually need to say started at 0. Do n equals 0, 1, 2, 3. So please make sure that you catch that. Start at 0, then go until you're outside 2 pi. So 0, then 1, then 2, then 3, maybe 4, maybe 5. Generally, I don't give you problems that are worse than 3. 0, 1, 2, and 3, that is to say. Okay. Share whiteboard. So example 3. And let's call this 3a. And I'm still going to just say solve. Sorry, I'm trying to find my problem. We got sine of 2x equals negative square root of 3 over 2. Don't hit buttons. Negative square root of 3 over 2. Now, the whole n equals 0, 1, 2, and 3 situation, that's if we have restrictions. This still does not have restrictions. So we'll still be adding the 2 in pi, but we're not going to go through n equals 0, 1, 2, and 3. Those notes were just for restrictions. Maybe we'll finally see that in example 3b. Hint, hint, wink, wink. All right, so this is what we were just talking about. The inside is not just an x. It's got a 2x or 3x or something like that. So this is where we need to do a substitution. We're going to say let theta equal the inside, which is 2x. This is a technique we learned back in 161, and I believe we even did it once or twice in here previously, not for solving equations. So by changing to theta, now this 2x is just a theta, so our equation becomes, that's a double arrow kind of used for transformations. So that's the sine of theta is equal to negative square root of 3 over 2. Well, this is a trig equation with a single trig term, and it is isolated. So we can go ahead and figure out what angle theta is based on the fact that its opposite is square root of 3 and its hypotenuse is 2 for a reference angle. Now this negative says that we're going to be in quadrants 3 or 4. based on a smart trig class because sine is negative in quadrants 3 and 4. Okay, so we can draw up our reference triangle. Here's our theta prime. And its opposite is square root of 3. Its hypotenuse is 2. This is our 1, 2 square root of 3 triangle again. Now it's opposite of the square root of 3 this time. So that says that the reference angle is pi over 3. Pi over 3. So our reference angle is pi over 3, but we've got to put that, we have to put that in quadrants 3 and 4. So again, to do that, to put something in quadrant 3, you're going to add pi, which is 180 degrees. Put something in quadrant 4, you take 2 pi, aka 360 degrees, and subtract the angle. So our first solution, let's call it theta 1, is actually pi over 3 plus pi, which is pi over 3 plus 3 pi over 3, which when you combine, you get 4 pi over 3. So that's the first solution in theta. This is our yen. Remember, we're going to have to go back to dollars. And then theta 2, let's put that here. That should be 2 pi minus pi over 3. So again, theta 1 was the quadrant 3 answer. Theta 2 would be the quadrant 4 answer. Getting our LCD, denominator 3, 1 goes into 3 times, 3 times 2 is 6. So that's going to be 6 pi over 3 minus pi over 3, which is 5 pi over 3. 6 minus 1 is 5. And that's our answer in quadrant 4. That's pretty ugly. Let's try that again. There we go. So that's just a single answer in quadrant 3. That's just a single answer in quadrant 4. But the problem is we were not given restrictions on this. So we have to add that 2 in pi because we're dealing with sine. So let's go up here. So we have to add 2 in pi to these. Terrible. While still in terms of theta, you have to do this before you switch back to your dollars, before you switch back to your x's. So your first solution, or let's just say this all together. That's going to be the 4 pi over 3 plus 2 in pi, or it's going to be the 5 pi over 3 plus 2 in pi. So again, these are the solutions, the infinitely many solutions in quadrants 3 and 4 in terms of theta. But we said our original problem was x, that's our standard dollar. We got to go back to the dollar. So make sure you go back to x. Now, you can only do this after putting those 2 in pi's in there. If you do that after, it's going to mess things up because the period under theta is different than the period under x. So, excuse me, instead of writing theta, we're going to write 2x because theta is 2x. So we'll go 2x. This will be the first one, equals 4 pi over 3 plus 2 in pi. Or we get, I'm just going to do a little squiggly here to separate my equations, the theta, which is 2x, equal to 5 pi over 3, plus 2 in pi. Now what we need to do is solve for x. How do we do that? Divide both sides by 2. Because don't even focus on the ugliness of the right-hand side of each of these. It just says 2 times x, the thing we want to solve for, equals blah, blah, blah. So 2x equals blah, 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 divide both sides by 2. Now, because there's multiple terms here, we have to do that for all the terms. So let me rewrite 2x equals 4 pi over 3 plus 2 in pi. So we're going to divide the 2x by 2, 4 pi over 3 by 2, and the 2 in pi by 2. For the other equation, the 2x equals 5 pi over 3 plus 2 in pi. Excuse me. We divide all of those terms by 2. Now, dividing by 2 is the same as multiplying by a half. These are compound fractions. We've talked about them. A fraction divided by another fraction means multiply by the reciprocal. So dividing by 2 is the same as multiplying by a half. So this is going to become x equals 4 pi over 6 plus n pi, or x equals 5 pi over 6 plus n pi, because the 2's cancel. Pen's being weird all of a sudden. In front of the x's and the n pi's. But this 4 over 6 reduces to a 2 and a 3. So that's x equals 2 pi over 3 plus n pi, or x equals, this one doesn't simplify, 5 pi over 6 plus n pi. Those are our solutions. So let's retread this problem because there's a lot going on. We originally had sine of 2x equals this value. Because there was a number in front of our variable inside, we did a substitution. Because now this just says sine of theta, sine of x, whatever, sine of y, it doesn't matter what the letter is. You can use any letter you want to substitute with. But what matters is there's no number in front of this now, which means we can go to this reference triangle, find the solution to that, put it in the appropriate quadrants, which gives us the solution in terms of theta. But we have to make sure we add the 2 n pi because this 360 degrees is related to the solution in theta, not the x. So once you have this, then you go back to your solution in x. So the theta has become 2x's. And then it was just simple algebra, divide everything by 2. And you might say this part right here isn't simple because you're dividing by a fraction by something else. But we've discussed that in class, multiply by the reciprocal. So that's how we got the 4 pi over 6 and the 5 pi over 6, reduced our fraction, and we got our solutions. So what's interesting here is, excuse me, the period here is only in pi for the additional solutions. It's not 360 degrees being added over and over. It's adding 180 degrees over and over and over. And that's because the period of sine of 2x is, guess what, 180 degrees. Remember, a period is always 2 pi for sines and cosines divided by the number in front of x. So I think it kind of makes sense that this happens, but some students will want to just go ahead and throw that in the end and not show the algebra, and they'll end up using the 4 pi over 3 and the 5 pi over 3 as the actual solutions, and it's wrong. They end up being 2 pi over 3 and 5 pi over 6, not 4 pi over 3 and 5 pi over 3. There's a lot of subtleties to this problem that you have to manage. You have to do things in the right order. So I suggest practicing this over and over and over, even if there is only one in my math lab. All right. So that was A. Let's do B. And this one is going to be the first problem where there is a restriction. Example 3, B. Solve on, say on, there's our hint that it's a restriction, bracket 0, comma, 2 pi, parentheses. That is a restriction. I have said that the domain for this problem is only in one full unit circle from 0 degrees to 360 degrees. We're including 0 degrees, but not 360 degrees because of the parentheses. Why are we not including it? Because that would represent the same answer. So instead of just saying, all right, we need the infinite answers, we're just worried about one go around. And the problem is going to be sine of 2x equals negative square root of 3 over 2. Man, that looks really familiar for some reason. Let's go back a page on my whiteboard. Sine of 2x equals negative square root of 3 over 2. Huh. Sine of 2x equals negative square root of 3 over 2. It's the same example. So we've finished this, right? Well, we've finished a lot of the work, but now we have the restrictions. So again, this is the same example, but with restrictions. So from before, the solutions, let me just do that. X equals 2 pi over 3 plus n pi and 5 pi over 6 plus n pi. But now we have to account for the restrictions. So this is where we're going to go through the letting n be 0, then 1, then 2, then 3, then 4, however many you have to do until the answer is past the bounds. Bounds being the 0 to 2 pi. So when you get an answer that's 360 degrees or larger, you stop. That's when you hit the brakes. So these are cases. So when we let n be 0, that's a 0, not a 2, or theta, that's a 0. That says that x is going to be 2 pi over 3 plus 0 times pi. See, this n, that's what I'm saying is 0, which is just 2 pi over 3. In the second case, this was the 5 pi over 6 plus n pi. So 5 pi over 6 plus 0 pi. Well, that's just 5 pi over 6. So n equals 0 is the answers that would be inside of your first or second or third or fourth quadrants without going around extra times, generally speaking. Okay, so those answers are less than 360 degrees, so we're going to move on to n equals 1. Oops. Gotta stop hitting buttons. So that's x equals 2 pi over 3 plus 1 times pi. Again, the n is now a 1. Getting an LCD, that would be 2 pi, oops, button, 2 pi over 3 plus 3 pi over 3. 2 plus 3 is 5, so that's 5 pi over 3. Let me box these up as we're going. And 5 pi over 3 is still less than 360 degrees. So that one's good. The other one would be 5 pi over 6 plus 1 times pi. Getting an LCD is 5 pi over 6 plus 6 pi over 6, which is 11 pi over 6. And that is still less than 360 degrees. 12 pi over 6 would be 360. It's when the top is double the bottom with fractions. That's when you know you're at 360. So if I got an answer that was 12 pi over 6, aka 2 pi, that would actually be too large because of the parentheses, but 11's fine. All right, so we've got 1, 2, 3, 4 answers so far. Let's try n equals 2. So this would be x equals 2 pi over 3 plus 2 times pi, because the n is now 2, which is 2 pi over 3 plus, that's going to be 6 pi over 3 when you get an LCD, which is 8 pi over 3. 2 times 3 is 6, 8's bigger than that, so this is too big. Now you might say, all right, well now let's try adding the 5 pi over 6, but 5 pi over 6 is bigger than 2 pi over 3. So guess what? We're already done. We know this one's too big, the next one's gonna be too big as well. And if you don't trust me, you can show the work. 5 pi over 6 plus 2 pi will be 5 pi over 6 plus 12 pi over 6. I mean, we're adding 2 pi, we're adding the number where we're supposed to stop. So I hope that that's obvious that it's too large, but either way, 17 pi over 6, definitely too big. Oops, buttons are hard. So our answers were the 2 pi over 3, the 5 pi over 6, the 5 pi over 3, and the 11 pi over 6. Okay. So again, this was the same example as last time, except we finally threw in restrictions. And restrictions are when you have to go through your n equals 0, n equals 1, equals 2, n equals 3 cases potentially. This is especially an issue when you have that number in front of the x. If this original problem was just sine x, I might not even have to do the n equals 0, 1, 2, and 3 cases. And we didn't even go to 3. 0 and 1 were the only ones that actually led to solutions. Now, here's kind of a spoiler. Generally speaking, the number that's in front of x is going to have some type of relation between how many n's you have to go through. I don't want to say what that is yet, but it's definitely there. Maybe it's because this is a 2, we had to go through 2 iterations of n. So if it was a 4, maybe we'd do 4 iterations of n. Maybe. But the complications here are really just getting LCDs, all that jazz. Do you have to do these in radians? I really prefer that. If you did them in degrees, I wouldn't count it wrong, but in my math lab, your answers are probably going to be in radians. So just make sure you understand how to deal with those. All right, so let's do, I think we have time for one more example. And then we'll call it a day. So we're going to solve on the restrictions 0 to 2 pi. Same restrictions as last time, but new example. 2 sine of x plus 1 in parentheses times 2 cosine of x minus square root of 3, close the parentheses, equals 0. So I mentioned back in the instructions in the text file that if you ever were able to factor, you should factor. Well, this problem's already been factored for you. Pardon my yawn. So we have something factored, which means we can use the 0 product rule, ZPR 0 product rule. Since these are set equal to 0. Now, if this wasn't a 0, we couldn't do that. We'd have to make it 0 somehow. So 0 product rule says just make 2 equations out of this. 2 sine of x plus 1 equals 0. or 2 cosine of x minus square root of 3 equals 0. Subtracting 1 on both sides for the first equation gives us 2 sine of x equals negative 1. Divide by 2, so that sine of x is equal to negative a half. Let's finish the other one. Add square root of 3 to both sides, which will give us 2 cosine of x equals square root of 3. Divide by 2, divide by 2, so that cosine of x equals square root of 3 over 2. So these are the two equations we're solving independently. Now this first one seems really familiar. If you go back to example 1, so sine of x equals negative 1/2. Here we go, example 1, sine of x equals negative 1/2. So this is the same equation. We don't really need to reinvent the wheel and do all this stuff again. Let's just say, by this example, the solutions were 7 pi over 6 and 11 pi over 6. But this had the adding 2 in pi's. We're not going to need that anymore because of the restrictions. So again, the solutions were 7 pi over 6 and 11 pi over 6. So by example 1, x equals, already forgot my numbers, 7 pi over 6 and 11 pi over 6. Notice we are not adding the 2 in pi's. And that was because this problem had restrictions. If you were to add any multiple of 2 pi, you're going to be bigger than 360 degrees. And again, because this didn't have the number in front of the x, we don't have to go through the n equals 0, 1, 2, 3 cases. You can, but you'll see that n equals 0 is the only one that leads to solutions in those restrictions. Okay, so cosine of x equals square root of 3 over 2. I do not believe we have solved that problem, so here's our reference angle. Cosine is adjacent of hypotenuse, so the adjacent square root of 3. Hypotenuse is a 2, and look at that, it's the 1, 2 square root of 3 triangle again, so the reference angle is pi over 6. But that's a reference angle. This was positive, so by a smart trig class, cosine is positive in quadrants when we're moving right, 1 and 4. So that means the reference angle is the first solution. So x equals pi over 6. That's a solution. And putting that in quadrant 4 would be 2 pi minus pi over 6. And we've seen that problem done before. That ends up being 12 pi over 6. 12 minus 1 is 11. So we get 11 pi over 6. So we got 7 pi over 6 and 11 pi over 6 from the first equation, the left parentheses, that is to say, being set equal to 0. And then we got pi over 6 and 11 pi over 6 from the second equation, the second of the parentheses being set equal to 0. But if you notice, 11 pi over 6 is a solution to both of them. We don't really want to write that twice. So our solutions all together is just x equals pi over 6, 7 pi over 6, and 11 pi over 6. I put them in ascending order. This is a 6 down here. So it ends up being 3 solutions instead of 4 because you found the same solution twice. There's no need to write the same solution twice.
back in pre-calc 1, we would talk about multiplicities of solutions and how they affected whether you bounced or crossed on the x-axis. But we don't really get into that type of analysis in here, so it's just information that passes us by. Now again, there are no adding 2n pi's in here because this problem had the restrictions. Also because there were no values in front of the x's inside the trig functions, I didn't actually have to go through the n equals 0, 1, 2, and 3 cases. If you wanted to have these be adding 2n pi, try out n equals 1, you will notice all of them will fail because you'll be adding 360 degrees to solutions, and adding 360 is bigger than that. The right-hand restriction of the domain, that's what I mean by that. Okay, so this has been interesting. I hope that everything has been understandable. As I said, this will be saved. I will be uploading it to YouTube immediately after this class. I have to teach my next class in about 15 minutes. So hopefully I have enough time to do my upload before that class starts. If not, the upload may not be up there until this afternoon. We have not finished 6.5. We still have 1, 2, 3, 4, 5 more examples to cover. So we may finish that on Wednesday. We may still be working on that on the following Monday. We shall see. But for now, we'll go ahead and call it a day. If you have any questions, you can email me. As I said, I'm going to set up some discussion boards in Canvas. I'm going to do that soon, if not today, tomorrow. That way, y'all can ask each other questions. I will occasionally chime in. I'm not going to be the only one. I'd like to see y'all helping each other out. And if I don't see an answer, then I'll come in and give an answer. But again, I hope this has been an okay experience. We're doing the best with what we can. And everyone have a good day. Stay safe. Stay as isolated as you can. And I will talk to you Wednesday morning at 8 a.m. Have a good day.
Thanks, Mr. Beckner. Not a bad job.
Appreciate it.